Before I define power series, I want to take a moment to review the ratio test. We'll see that this test will play a big role when we start to talk about the convergence or divergence of power series. So the ratio test focused on a limit of successive terms in absolute value for a series whose terms say are a sub k. Let's call this limit L. So again, this is the limit of the absolute value of a sub k plus 1 divided by a sub k as k goes to infinity. Then, looking at that value of L, if it's strictly less than 1, then we said that the series converges. If that limit is strictly greater than 1, then the series diverges. And then we saw that we had to be cautious. If the limit were exactly equal to 1, the ratio test really gave us no information. Consequently, the series might converge or it might diverge. So we will be using this ratio test to apply to a class of series that we're going to refer to as power series. So let's first of all start off by defining these. A power series, again, we're going to see some familiar phrasing here, centered at x equals a, is a series of the form sum from k equals 0 to infinity of c sub k times x minus a to the k. So a couple things to point out here. This c sub k we refer to often as the coefficient. And while it could be constant, it really could depend on the index k. And this A we see is what we're referring to as the center. And so we see that we get a general structure here for a power series. So let's look at some examples of things that are power series and try to match it up to this structure that we've defined. First of all, if I have the sum from k equals 0 to infinity of x to the k divided by k factorial. This is a power series. And if I wanted to identify the terms here, I can see that my center, a, would have to be 0. That's because x to the k is the same thing as x minus 0 raised to the k. And if we're trying to figure out the coefficient, we look at what's being multiplied by, in this case, x minus 0 to the k. That would be 1 over k factorial. Another power series, the sum from k equals 0 to infinity of the factorial of 2k times x plus 2 to the k. Notice here that because I have an x plus 2, in order to fit that into the x minus a framework, that means a is a minus 2. And again, the coefficient should be what we're multiplying by this x minus a to the k factor. And in this case, that's the factorial of 2k. And a slightly more challenging example, consider 2x minus 4 raised to the k over k plus 1 squared. The reason this one's a little bit harder is notice that it's not already in the structure of simply x minus some value a to the k. So if I'm identifying the coefficient, I have to have it multiplied by this kind of factor where the coefficient inside of the x minus a on x is simply 1. So looking at this, I can rewrite these terms to force it into that structure. In particular, 2x minus 4 is equal to 2 times the quantity x minus 2. So that numerator, since it's all raised to the k, is the same thing as 2 to the k times x minus 2 raised to the k. The denominator is k plus 1 squared. So notice a few things here. I can see that the value of a, my center, is positive 2. And likewise, I can see that the coefficient now is, in fact, 2 to the k over k plus 1 squared. So if I hadn't rewritten that, I could have convinced myself that the coefficient was simply 1 over k plus 1 squared, but I see that that 2 to the k is actually part of it. The other thing I'll point out about the center in every one of these cases And notice that it's always the value of x that you can plug in that effectively results in 0. So that's another kind of quick way to identify the center of our power series.